Hello good people, I'm going to spend some time talking about physical changes and chemical changes. In order to explore physical changes, I'm going to bring in water as an example. And here it is. I have an iceberg floating on some water, and presumably I also have some water in these clouds as well. I could make the argument that in this photo, water exists in all of its three states. It exists as a solid in form of this ice, it exists as a liquid in form of this sea or lake, I presume it's a sea, and it also exists as a gas or vapor in form of these clouds. But keep in mind that air can contain water vapor or water gas even if we do not perceive any clouds. Now let me bring in a simplified cartoon of the three states of water. So at the top, I have water as a gas. This is also often referred to as water vapor. In the bottom right, I have water in its liquid state. And to the left, I have water in its solid state, commonly known as ice. Now, when water vapor or water gas cools, so when we go from gaseous to liquid state, we are talking about a process known as condensation. If the liquid is cooled even further, eventually we will end up with ice. This process is known as freezing. I could also start with water gas and cool it so quickly that it doesn't actually go through the liquid state. So I could go from a gas straight to a solid. This process is known as deposition. What if I start with solid water? So what if I start with ice and I increase the temperature? Well, if I increase the temperature slowly, I will end up with a liquid. And this process is known as melting. If I then continue to heat up my liquid, the liquid will eventually turn into a gas. This process is known as vaporization. Now, under certain conditions, I can go straight from a solid state to a gas state. So I can go from solid to gas. And this process is known as sublimation. The thing to note though is that as I go through these processes, so as I change from gas to liquid to solid state, the nature of water does not change. I'm still dealing with water in all three cases. Except here, when I have ice, I'm dealing with solid water. When I have vapor, I'm dealing with gaseous water, and when I have liquid, well, I'm dealing with liquid water, the one that we are most commonly familiar with. But in all cases, it is still water. I'm still talking about molecules of water. They have not changed. So when we talk about physical change, we are talking about a change in state. We are talking about something going from being a liquid to being a solid to being a gas, or in any other direction. So in terms of a definition, we could say that physical change is a change in the physical state, but not a change in a chemical composition or identity of a particular substance. Great. Well, if this is physical change, what in the blazes is chemical change? Before I look into that, I'm going to spend some time exploring water a bit more, because water is rather special. So let me get rid of this and bring in a molecular representation of water in its three states. And here they are. So on the left, I have gas, in the middle, I have liquid, and on the right, I have solid. When I'm dealing with water in its gaseous phase, all of the water molecules are moving independently of each other. So I can grab this one molecule and move it around. So it's moving on its own. It doesn't interact much with the other water molecules. And they are fairly spaced apart. When I deal with water in its liquid form, the molecules still move around a fair bit, but now they interact with each other a little bit. Okay, in fact, they interact with each other quite a lot. And we will talk about this interaction later on. The point is that they are no longer completely independent. They are somehow interacting with other water molecules. And they are much closer together than when in a gaseous state. What about water in its solid state? Well, now the molecules are actually locked into place, and they cannot move as freely as is the case when they're in gaseous or liquid states. They can vibrate a little bit, but their motion is rather limited. And so they form this lattice structure. So let me write that down. We are talking about a lattice structure, sometimes also referred to as a crystal lattice. Please note the spelling, lattice, not to be confused with lettuce, which I know with my accent sounds a little bit the same. So once again, it's lattice, not lettuce. Now, why am I spending time talking about this? Well, it turns out that the crystal lattice that is formed is such that the water molecules are actually further apart from each other than when they are in the liquid state. So even though it may not come across in my fantastic drawing, the individual water molecules are actually closer when they are in liquid state than when they are in the solid state. This means that solid water, or ice, occupies more volume than the same amount of liquid water. Water expands upon freezing. Do not believe me? Well, place a bottle full of water in a freezer overnight and see what happens. Actually, do not do that. I do not wish to get sued. Getting back to the point though, the result of water expanding upon freezing is that solid water is less dense and thus floats on liquid water. And you have seen this when you place an ice cube in your drink. The ice cube floats, just like a giant iceberg floats on water. The fact that water is less dense in its solid state than liquid state is rather unusual. And there are only few other substances that share this property. Off the top of my head, I can think of acetic acid and germanium. Well, that was a slow walk down a windswept beach to a cafe that was closed. Moving on. So physical changes are changes in state. How are they different from chemical changes? Or how are chemical changes different from physical changes? Well, let me get rid of this and bring in a few examples. On the left, I have some copper pipes or pieces of copper pipes, and on the right, I have some iron chains. Both of these have undergone some changes. If I look at the copper pipes, the one on the far left is shiny, while the one next to it has been tarnished. If I look at the chains, the ones on the far right are shiny, whereas the ones on the left side have rusted. And here is where we have to be careful about how we use the language. In everyday language, you might say, oh well, they've physically changed because physically they look different. However, in sciences, this is not considered a physical change. This is considered a chemical change. Why is that? Well, let's look at copper first. So this shiny copper pipe will be installed somewhere, maybe under a sink somewhere. Over time, this copper pipe will react with the air, or more precisely, it will react with the oxygen in the air. So I could write that copper will combine with oxygen. And as that happens, I will end up with copper oxide. It is the copper oxide that is responsible for the tarnish on the copper pipe. The thing to note is that copper oxide is now a completely new substance with its own properties. What about the iron chains on the right? Well, a similar process takes place. I will have iron, and over time, it will react with the oxygen from air. And that will give iron oxide, most commonly known as rust. And here too, the iron oxide will have its own set of properties that are different from the properties of iron and oxygen. In both of these cases, we had a chemical reaction. On the left, copper reacted with oxygen to give copper oxide. On the right, iron reacted with oxygen to give iron oxide. So we had a chemical reaction. And whenever you have a chemical reaction, you also have a chemical change. Let's look at another example. In this example, I'm going to start with a raw egg. I can choose to boil this egg, which means I will end up with a boiled egg, Or I could choose to fry this egg, in which case I will end up with a fried egg. Is this an example of a chemical or a physical change? You might be tempted to say that this is an example of a physical change. And your argument might be something like this. In case of the raw egg, the egg white is runny, it is liquid. By the time I have boiled it or fried it, the egg white has become solid. So you might argue that what we are seeing is just a change of state, so therefore a physical change. However, there is more going on here, and this is an example of a chemical change. The compounds found in the egg white and the yolk have actually undergone a chemical reaction to give you your boiled egg or your fried egg. So sometimes a chemical change might be followed by a perceived change in state. So what would be a useful definition for chemical change? A chemical change is a change due to a chemical reaction that alters the chemical composition of a substance. So in these examples, the copper that has become copper oxide no longer has properties of copper. The iron that has become iron oxide no longer has properties of iron. And the compounds found in a raw egg have reacted to give a boiled egg or a fried egg, and as a result, those compounds have changed. They no longer have the properties they had when they were in the raw egg. In summary, a physical change is a change in state. So when I go from a gas to a liquid to a solid, the identity of the compound that changes the state does not change. So in case of water, if I have gaseous water, ice, or liquid water, it is still water. Chemical change, on the other hand, is a change due to a chemical reaction. And in the process, the identity of the compound changes as well. That is all for now, and I will see you on the flip side.